distinguishing luster and their property to be able to make sheets and wires ductility. These metals conduct heat and electricity. Metallic oxides are basic and these are ionic or covalent compounds. Metals form cations in aqueous solutions. If we dissolve the salts of these metals, they produce cations in aqueous solutions. Opposite to it, nonmetals are non-lustrous and they make colored salts. In pure form, nonmetals are brittle and hard. They are poor conductors of heat and electricity. Their oxides are acidic in nature. Their salts in aqueous solutions make anions and oxyanions. These are certain properties that distinguish between metals and nonmetals, and our metalloids lie somewhere in between these two. Physical properties. Next is we are going to talk about the boiling point of a very important nitrogen compound known as ammonia, which is nothing but a hydride of nitrogen, and another compound known as phosphine. It is a hydride of phosphorus. While comparing the boiling point of these two compounds, we saw nitrogen hydride ammonia having a fairly high boiling point compared to phosphine. The reason is nitrogen having a unique property to make hydrogen bonds. Because of these hydrogen bonding capacity, these molecules are strongly bound to each other, results in stronger or better boiling points than phosphine. Phosphine attached to another phosphine molecule through van der Waals forces, which depends upon the atomic mass of a molecule and its size. So these are relatively poor or weak force compared to hydrogen bonding. That is the reason their boiling points are low. We are going to talk about chemical properties of group 15 elements now. Oxidation state possible for these elements are from -3, which is possible through acceptance of electrons or by donation of valence electron, which are 5. So maximum level half-filled p orbital to make +5 oxidation state. This is the outermost electronic configuration of any group 15 element, having fully filled s orbital and half-filled p orbital. When these elements accept 3 electrons, they make -3 oxidation state. When they donate completely all the electrons, they make +5 oxidation state. These are maximum possible oxidation state or minimum possible oxidation state. +5 is the maximum possible oxidation state. -3 is the other end of oxidation state, the negative side, after reduction. This is the oxidation side oxidation state. Tendency to exhibit -3 oxidation state reduces down the group. The reason is low electron activity down the group. As we move down the group, as we saw in the properties, what we observed, electron activity reduced down the group. In such a case, heavier elements will not be able to attract electrons toward themselves from any other molecule or ion. Now the stability of these oxidation states. First, +5. Stability of +5 oxidation state reduces down the group, and +3 oxidation state increases. The reason for this is inert pair effect. What it is? Inert pair effect is reluctance of s orbital electrons to participate in chemical reaction. Like for bismuth case, it shows very strong inert pair effect and stability of +3 oxidation state. Bismuth 3 positive cation is fairly more stable than bismuth 5 positive cation. Why these elements exhibit such an effect? The reason is bismuth having a 4f and 5d electrons in its inner core, or the electrons lying in between the outermost shell and nuclei. We know 4f and 5d orbitals have poor shielding effect. Because of poor shielding effect, outermost electrons experience considerably higher effective nuclear charge. In such a case, the s electrons, we know s electrons experience greater pull of nuclei compared to other orbitals. It reduces from s to p to d to f. So s electrons in bismuth in the outermost shell experience considerably greater nuclear force, and they are tightly bound to the core. Because of their high binding energy, the ionization enthalpy will be high for those last two electrons. That is the reason bismuth tried to exhibit +3 oxidation state with greater stability compared to +5 oxidation state. So this is a +5 oxidation state for bismuth, which is having a low stability compared to +3 oxidation state. Now, as +3 oxidation state in case of arsenic, antimony and bismuth become increasingly stable down the group, there is another property known as disproportionation, where higher oxidation state like +5 decompose to give us +3 oxidation state. +5 decompose to give +3. The bismuth compound, bismuth pentafluoride, is unstable, and it tried to decompose to give us +3 oxidation state. Same phenomena in case of nitrogen. All oxidation states from +1 to +4 have low stability, and they try to disproportionate in acidic solutions. Let's take an example of nitrous acid. It having a +3 oxidation state, it tried to decompose or disproportionate into nitric acid having a +5 oxidation state and nitric oxide +2 oxidation state. So it simultaneously go to oxidation as well as reduction. Next, the binding capacity of nitrogen. Nitrogen can form maximum 4 bonds. The reason is outermost shell or valence shell contain 1s and 3p orbitals only, which are available for bonding, compared to its heavier elements, into 15 elements, having empty d orbital in their valence shell. So they can use their valence shell d orbitals to extend their octet or accepting electrons from ligands or ions or molecules. That is the reason they can extend their covalency to make higher compounds. This is nitrogen. Only 4 orbitals are possible. It can't extend because 2d is not available. So it can make maximum 4 bonds. Only 4 atoms or molecules can be there around nitrogen. Here is a case for phosphorus, which having a empty d orbitals as well as half-filled p orbitals. So what can happen? One electron from here can be promoted to the 3d orbitals. Then we having a 1, 2, 3, 4, 5 orbitals present. And these unpaired electrons can pair up with the fluoride anions, as well as one fluoride can donate its pair of electrons here to make PF6. That is the reason PF6 is an anionic entity. It's all possible because of presence of empty d orbital. Molecular nitrogen comprises 78% by volume of atmosphere. So our atmosphere, 78% of it by volume is nitrogen, which is diluting the oxygen present in it. Nitrogen is found in proteins, plants and animals. Protein makes plants and animals, and this nitrogen is a backbone of it because it is used in these linkages, CONH bond linkages. In the Earth's crust, these nitrogen exist as nitrates like sodium nitrate, chili saltpeter, or potassium nitrate, Indian saltpeter. Nitrogen got certain unique properties. These unique properties of nitrogen are because of its exceptionally small size, which is roughly half of the atomic radii of the heaviest element that we are going to consider here, bismuth, for chemistry. It's almost double of the size. Bismuth atomic radii is almost double of the size of nitrogen. Nitrogen has a unique ability to form p-pi multiple bond with itself and with the other elements which having a small size or comparable size like carbon, oxygen and fluorine. So we having a one sigma bond, nitrogen overlapping, and 2 pi bonds. So nitrogen got basically diatomic molecule having a fairly high bond enthalpy. This is 941.4 kilojoule per mole, which is fairly high and not easy to decompose. Nitrogen do not have d orbital, so it cannot expand its octet to form d-pi, p-pi bonds like other elements like phosphorus, arsenic, antimony and bismuth can do. They can extend their octets to form a d-pi, p-pi bonding, but this is not possible for nitrogen. Its covalency is 4 only. Due to the small size and in bond length, there are high interelectronic repulsions of non-bonding electrons. This is the reason nitrogen atoms do not exhibit catenation. Like carbon show catenation property, where carbon-carbon-carbon chains can be there, but such chains do not exist for nitrogen. The reason is nitrogen got lone pair of electrons. Those lone pair of electrons create a lot of inter-electronic repulsions, and these are the reason for inability of nitrogen to show catenation. That's what we see. Our 2s electrons here, these are the electrons. They show inter-electron repulsions. Now, nitrogen we saw form p-pi-p-pi bonding because of effective overlapping of p orbitals with the same size atoms, but heavier elements of this group do not show p-pi-p-pi bonds. The reason is their atomic orbitals are so large and diffused in shape that effective overlapping is not possible. For p-pi-p-pi bonding, there should be effective overlapping of p orbitals, but this is not possible because of their large sizes make it impossible for the effective p-p orbitals overlapping between the two phosphorus atoms, p orbitals, or two arsenic atoms, outermost p orbitals. That is the reason p-pi-p-pi bond do not exist for heavier elements. All these four elements do not show p-pi-p-pi bonding for the same reason, large size of their atomic orbitals.